Let us now relate what we just learned about polar curves to what we learned previously about parametric curves by showing that any polar curve can be thought of as a parametric one. So recall that by the conversion formulas, we can relate the Cartesian coordinates of a point to its polar coordinates as follows. X is r times cosine theta, y is r times sine theta. Now, if this r here corresponds to a polar curve, it means that r is a function of theta. So the two equations become f of theta times cosine theta and f of theta times sine theta. So this means that we have a pair x of theta, y of theta, and so this pair is the point, the coordinates of a point on our curve. And so if the curve has this form r equals f of theta, then a point on it can be written in this form, x of theta, y of theta. And so what this means is that we can think of theta as our parameter. So previously we would think of parameter as the time, and it would indicate the position of a certain moving particle. Now here, parameter is just the angle that a ray that points towards the particle forms with the polar axis. And then we obtain that our polar curve r equals f of theta is in fact parametric with parameter theta and specific parameterization that we have in mind here is the following. X equals f of theta cosine theta and y equals f of theta sine theta. And so this means that we can do with polar curves anything that we are able to do with parametric curves, just because a polar curve is a special case of a parametric curve with this particular parameterization. So for example, since we know how to compute slope of a parametric curve at a particular value of theta, it means that we can determine the slope of a polar curve as well. And so the way to do it is to recall that the slope is given by dy over dx evaluated for some theta, right? And that just means we have to differentiate dy over d theta and divide that by dx over d theta. And so we can easily do this using the representation we obtained for the polar curve here. And so we have dy over dx is equal to, if we think of this function f here as just, if you just denote it by r, right? So that's the r of theta here and here. So we are not going to introduce a separate notation for the function. We'll just say that, okay, r just depends on theta, and that's written right here. So dy over d theta can be computed using the product rule. So we have in the numerator, we have r prime times sine theta plus r times cosine theta. So that's the derivative of this product we have for y. And in the denominator, we differentiate x in a similar fashion. So we have r prime times cosine theta minus r times sine of theta. And so this here gives us the slope of a polar curve for a specific value of theta. We can simplify this a little bit when we want to compute the slope at the pole or the origin. So for the origin, r equals to 0, and that's the way to characterize the origin in polar coordinates. R must be equal to 0. And so dy over dx at the origin is equal to what this expression becomes when r is 0. And well, these two terms vanish. So we'll just have r prime sine theta over r prime cosine theta, and then r prime will cancel out as well. So we have sine theta over cosine theta, and so that's just tangent of theta if r prime is not 0. So that we can cancel it out. And so this simplifies computing slope of a curve at the origin. And so using this expression for the derivative dx over d theta and dy over d theta, we can go ahead and derive the formula for arc length. So if we recall that the formula for arc length of a parametric curve gives that length of a curve, in the general case parametric, is given by the following expression: dx over d theta squared plus dy over d theta squared integrated with respect to theta. So this is the general expression for the arc length of a parametric curve that we derived previously. Now, in our case, it becomes, after some simplification, which I will omit. So basically, what you have to do is to take the expressions for dx over d theta and dy over d theta and plug them into this square root. And then after some simplification, we will obtain that L is equal to the integral from angle alpha to angle beta square root of r squared plus dr over d theta squared integrated with respect to theta.